Okay, I want to talk about a few concepts here before your third exam. So as usual, I've got the exam 3 prep file open, just on that first page here. Again, as before, spend more time with the concepts than you think you need. Um, Generally speaking, students, and I've said this before, but they love working examples. They love working problems. You feel good about it because you get an answer and you did it right, and that's good. And the concepts are a little bit harder to study for. I totally get that. Um, but just make sure you spend more time than you think because I want to make sure you bias towards those concepts. There's a lot of concepts on this exam. I could give an entire exam of nothing but concepts. We talked a lot about them in the previous videos. Um, the worksheets this time talked a lot about them. There were a lot of uh, now we're talking about the true, sometimes false type situations. There's a lot happening here, and we'll talk about some of those specifics again here today. Um, but just make sure you're on top of it here. One of the key things that I'm trying to teach in this course, hopefully you've learned, and if not, you've got just the last little bit here of time to kind of try to figure it out, is logic and critical thinking. And that's what a lot of these concepts ask you to do, and that's what we're trying to develop in you, are those skills. And so spend a lot of time there. It doesn't mean ignore the examples, right? Work through those problems, but spend more time than you need with the concepts. It's my kind of little words of wisdom here as you're studying for this third exam. So we start off as usual, know all of your symbols. A couple of things from previous exams, central limit theorem. Remember that the central limit theorem says that as my sample size gets bigger, the distribution of sample means approaches a normal distribution. That's important because that's going to be one of our foundational assumptions that we're checking in means hypothesis testing. Know the properties of those distributions, still know those. Some of them pop up within the actual problems themselves. But also those are just good concepts that are foundational to the entire course. So make sure you still know those. Um, Remember, a binomial is, we have those four characteristics, right? Fixed number of trials, independent trials, constant probability of success and failure, and there's only two options that cannot happen at the same time. Right, binomial is discrete. Distribution normal is a type of continuous distribution. Z and T are subsets of normal, right? Normal, Z, and T, just they're bell-shaped distributions. Normal is whatever mean and standard deviation it has. We just know when we see normal, all we know is bell-shape. We see Z, we know bell-shape, plus we know mean of 0, plus we know standard deviation of 1. T, we know mean of 0, but there's an infinite number of T distributions, and all of them have a standard deviation larger than 1. Talking about hypothesis testing, so this was the first thing that we covered here in this material. Um, our hypotheses, make sure that we know that only parameters go in the hypotheses. So know what a parameter is, right? That's why we've been talking about that all semester, right? Knowing what symbols are what, which ones have sample in front, which ones have population in front, knowing that all the ones that say population in front are parameters, all the ones that say sample in front are statistics, right? The whole idea of a hypothesis test is we're going to start off with a question about a parameter. We're going to do some work with our statistics to then come back at the end and make an inference back on that parameter that we started talking about, right? So think of it like a sandwich, right? Parameter, statistics, parameter, right? We start off on our hypotheses with our parameters. Make sure we know that there's some form of an equal in the null. It can either be just equal or greater than or equal to or less than or equal to. And then our alternatives do not have an equal, so it's not equal to or less than or greater than. Assumptions and why we care about them. So the assumptions are very, very similar to what we did for probability questions and confidence intervals. And why we care about them is the same reasons as before. So this is the idea we've talked about before, that it's kind of the same stuff over and over again. So hopefully it's kind of really setting in if it hadn't already, right? We want to know about the distribution of the sample statistic that we're building everything around. In a confidence interval, or let's start back in a probability. In a probability question, we said probability of X bar, probability of P hat. We needed to know stuff about what we were asking you probability about. We needed to know what the distribution of X bar is and what P hat is. And we said distribution the sampling distribution, right? We said we need to know what all the X bars could look like and all the P hats could look like. Why? So that when we got our one, we could kind of say, was it weird or not weird? How likely was it, right? It goes back to the idea we talked about a long time ago. You don't know what your temperature is. You don't have a database of what all the possible temperatures you could have are, but we have data on that, and you know what a reasonable temperature is, right? So that way, when you take your temperature one time, you know, is this really weird or not? Is this really unlikely, or is this really normal, right? And so it's this idea of you don't have to do it a bunch of times, but you know the concept, you know what temperatures are like. And that's the thing. When we talk about X bar or P hat, we say, what is X bar like? That's what we say with distribution. What's it like? Where's it located? How spread out is it? What kind of shape does it have? Okay. That carried into confidence intervals. We built the confidence interval around X bar and P hat. And we said we need to know what those are like to help us build the interval that say that in general, I think that the mean is between here and here. I think the proportion is between here and here. We go to hypothesis testing, same concept. We're making a hypothesis about mu or a hypothesis about P. And when we make those hypotheses, then we're going to actually do the work based off the corresponding sample statistic, X bar or P hat, but we need to know what it's like, just like we did before, nothing different. Okay, and so that's why we say we need to know, is X bar normally distributed? Is P hat normally distributed? Okay, if so, that's what allows us to use our Z table, our T table, or Excel or graphing calculator, do the same thing, right? To get critical values and P values, right? Make sure you understand big picture. I want you to understand what's really happening here. You're not going to be as successful if you're prepping for this exam and you're saying, I know how to do all the individual little pieces, but I don't really know what it means and how it fits together. That's what I want you to get through all of this is I want you to be able to say, when I get a critical value, where did that critical value come from? It came from a Z or a T distribution. Well, why was I able to use a Z or a T distribution? Well, because when we talk about X bar or P hat, we've checked our assumption. We've said those follow a normal distribution. Z or T is a normal distribution. See how that links up, right? So just like before, why we care about it when we did probabilities, when we did confidence intervals, and now that we're doing hypothesis testing, we care because when we use our Z and our T table for critical values and for P values, we're using a normal distribution. So we need to make sure X bar and P hat have a normal distribution. How do we check that? Kind of the same as before, just as a little refresher for you. X bar is normally distributed if X is normally distributed. So if you start off with normality, X bar is normal, you're good to go. If not, then we say we need to make sure we have a big enough sample size to use the central limit theorem. That's where we say if we know nothing about what X looks like, we'll just use 30 as big enough. But in reality, we are looking at both in and what the initial distribution looks like. If that initial distribution of X is really skewed, it's going to take a long time, a lot of samples, a big N, for X bar really get normal. Maybe you need a sample size of 40 or 45 or 50 or something like that. And as before, I'm not going to try to trick you. I just want you to understand this concept of if we start off with a skewed distribution and a sample size of 35, 35 is not big enough. Or vice versa, if we start off with a symmetric distribution, which is closer to normal, and we have an N of 25, that's fine. Okay. Now, if we don't know anything about the initial distribution, so look in the work, read the problem, pay attention to those details. If you read the problem and you see nothing about the shape of X, it doesn't say it's skewed, it doesn't say it's symmetric, there's no picture, nothing like that, then we just gotta use 30 as a cutoff. But if we know something, we have to use that to our advantage. Okay. And then we talk about P hat. What its distribution is, we're always going to make sure that X is binomial. So check through those four things. Ask yourself those questions. Ask yourself, do we have a fixed number of trials? Are the trials independent? Are there only two possible options? And is the probability of success constant? Ask yourself those questions. You're more likely to catch if there's something there. If not, if that's good to go, great. That's the first thing that we got to check. N times P naught and N times Q naught. So N times the P and the 1 minus P that come from the null hypothesis. As before, we are always checking if we have a good sampling methodology. That has nothing to do with normality. Those are two independent concepts. The idea there is just the fact that the whole point of this course, right, is we take a sample. It's a small thing. We make an inference on a big population. If we have a good sampling, we say, yes, we can make that jump, that inference. If we don't have good sampling, then we're a little bit concerned about that jump. So it's a separate idea, but it's just something else we're also checking. Make sure that we don't have any of those three biases. As I said before, ask yourself those three questions. Don't just say, it seems fine, right? Say, do we have sampling bias? Does my sample seem to have the same characteristics as the population that I'm trying to make an inference about? Do I have response bias? Is there a reason that someone would have lied? Is there a reason someone maybe just forgot? Are the questions asked in a way that people may not be giving good answers, whether they're being tricked or not? It kind of is irrelevant. It's just, are the answers good? Are the responses good and accurate? Or do we have non-response bias? And that's the idea that we asked for a lot of people's responses and we didn't get very many back. We always have to be a little bit concerned in those situations because we may have only got responses from the extremes of people who care, and we may be really missing what's actually happening because we're only getting a small piece of the picture. Okay. Know what failure of assumptions means. As with any of those things that I just kind of rambled on about there, if we have a big issue with our assumptions, we have a big issue with our results. If we have a small issue with our assumptions, we have a small issue with our results. I always like to say that the validity of our results is directly proportional to the validity of our assumptions. So if you say my assumptions are good, my results are good, and say that. If your assumptions are mostly good, but there's a little something to be concerned about, say my results are probably good, I just have a little bit of something just to kind of keep an eye on, right? If my assumptions are really bad, then I say, I got these results, but I don't trust them at all because the assumptions are problematic, right? The assumptions are like a foundation of a house. Everything that we do is built off of that, right? It's that idea that if I use a normal table, a Z or a T table, to get a p-value or a critical value, but I say X bar is nowhere near being normal, it's like, well, you used a number, but the number doesn't make sense because you needed normality and you didn't have it at all. Okay. Be able to use both rejection region and p-value methods. As you saw in the homework, there will be questions that just say find a p-value or what's the critical value. So be able to do both methods. If you do see a problem that doesn't specify, you get to choose. If you don't happen to see one, then you may be kind of forced to use one or the other. You never have to work both methods on any problem. I do that in the notes just so you can see both, so you can focus in on whichever method might be giving you a little bit more of a harder time than the other. Know what a p-value is. P-value is probability of getting a test statistic as extreme or more than the one that came from the sample under the assumption the null hypothesis is true. It's a basic definition. I can recite that to you extremely quickly because I've said it so many times. You need to say it to yourself so many times that you can recite it that way. It's a very basic concept of this course. I want you to know what a p-value is. Of course, we can also talk about a p-value. We say probability of getting a test statistic. You could also say a sample statistic, sample data. There's a couple different ways you could talk about that. Again, understand the key concept of the course. The idea is we're going to take a sample, boil it down to a statistic or some statistics that matter. We're going to convert that into a test statistic, and that test statistic is going to tell us something to make an inference. So when we talk about what a p-value is, you can kind of use that same idea of it's the probability of getting a sample, sample data, sample statistic, test statistic. It's the idea of the probability of getting what we use to make a decision as weird or weirder than what we got, right? As extreme or more than what we got, under the assumption the null hypothesis is true. Know your decision and conclusion statement. So just be able to wrap up the problem, right? Know that we have two options when we get a p-value. Your p-value is less than alpha, you reject the null. Your p-value is greater than alpha, you fail to reject the null. With the rejection region method, your test statistic falls in the rejection region, you reject the null. Your test statistic doesn't fall in the rejection region, you fail to reject the null. It's that simple. Okay, just know there's no tricks, there's no ifs, ands, or buts. That's as straightforward as it can be. If you reject the null, that means you conclude the alternative. If you fail to reject the null, you cannot conclude the alternative. Make sure you know how that works out. It's kind of very formulaic, so it's going to be, some of you are going to like that, some of you aren't. So whether that kind of speaks to you or not, that's the way it is. We have to make sure we understand how the process works. We never accept the null. And make sure when we talk about concluding, you're not concluding the alternative, that you pull back the symbol from your alternative, right? It has nothing to do with the claim. Ignore whatever the claim was. We throw that out and we come back and we either say that we can conclude, write out the alternative, or we cannot conclude, write out the alternative based off whatever you said about the null. That's based off whatever you got from your p-value rejection region, okay? Significance level, how would you choose one? We talked about this previously. You had an example of it on your worksheet. It's this idea that I know that type 1 and type 2 error go the opposite direction, and I have to read the problem and I have to say at times, is there a situation where type 1 error is worse than a type 2 error? Or is there a situation where a type 2 error is worse than a type 1 error? And you say to yourself, if a type 1 error is really bad, I don't want to make that. If I don't want to make a type 1 error, I want its probability to be small. I know alpha is the probability of making a type 1 error, so I would choose a small alpha. I would choose 0.01. If I don't want to make a type 2 error, I can't choose beta. I know I don't want that probability to be high. I know that's beta. I want beta to be low. I can't choose beta. We can't calculate beta. We can never calculate beta in this course that we've talked about. It can be assessed and hypothesized about what it can be. It's beyond the scope of this course. So for our purposes, beta is not something that can be calculated. And so you say, well, if I don't want to make a type 2 error, I don't want beta to be high. I can't choose beta, but I know alpha and beta move in opposite directions. So if I don't want beta to be big, I want beta to be small, then I need alpha to be big. And that's where we said, what is big? Well, we kind of cap off at about 0.1, right? Or go to the bottom of your G table, right? The three significance levels are 0.01, 0.05, and 0.1. Pick the bigger of those. Don't pick an alpha of 0.9 or something like that. That wouldn't make any sense. Again, big picture, right? It's a probability of making a type 1 error. You never want to make any error 90% of the time, right? So choosing an alpha of 0.9 wouldn't make any sense. Power type 1, type 2 errors, right? Know that all of them have two pieces. What did you decide and what the truth was? When you talk about power type 1, type 2 error, if you are not talking about both pieces, you're missing something and it's wrong. It's the probability of something happening, and that was power's probability of rejecting the null, and that was the right decision. Type 1 error is I rejected the null, that was the wrong decision. Type 2 error is I failed to reject the null, that was the wrong decision. You got to have both pieces. Okay, so know those, be able to define them, be able to identify them in the context of a problem. You've seen plenty of examples doing both. And then we talk about regression, be able to identify which variables which, the x and the y, right? The x is the one that is independent, the y is the one that depends on the other one. Properties and names of R and R squared, right? So R is our correlation, or sample linear correlation coefficient. R squared is our coefficient of determination. Properties, right? R is between -1 and 1. 1 is a perfect positive linear correlation. -1 is a perfect negative linear correlation. Zero is no linear correlation, right? And R of 0 doesn't necessarily mean there's no correlation, just means there's no linear correlation. So we talk about the whole sometimes true, always true type thing. Know what the things are saying and what they mean and what they don't mean. All right. Again, there's a lot of logic games we've got to play here, and it's not meant to be tricky. It is complicated. It's not meant to be tricky, but it is a complicated concept. So spend some time with that. Look back over that last worksheet that was provided for you if you need a refresher there. Relationship between R and B1. Remember, B1's the slope, B not B0 is the y-intercept. Remember that a positive slope implies a positive correlation. A positive correlation implies a positive slope. And negative as well, it applies as well. But a large slope does not imply a large correlation. A large correlation does not imply a large slope. They're two different things, right? Correlation is how close are the points together. Slope is how tilted are the points. Those are two different things. The signs have to be the same though, because a positive correlation means you're going up as you go left to right, and a positive slope means you're going up as you go left to right. So the signs have to be the same, but the numbers don't mean anything at all. Okay, so make sure you remember that. When to use the regression equation to predict values. Remember that we want to only use the regression equation for prediction if we are not extrapolating. What that means is we're not predicting outside of the scope of where the x's are, right? If x goes from 5 to 20, maybe you can make a prediction for 4, that's fine. You can make a prediction for 21, that's fine. If x goes from 5 to 20, you don't want to make a prediction about 40. That's too far out. We don't know what's happening out there. Okay, so we only want to make a prediction as long as the value that you're predicting for is within the range of values that you have data for, right? That's hopefully a common sense kind of idea. You also only want to use the regression equation for prediction if you see a scatter plot and the line seems to fit the points pretty well. Just the eye test. Look at the plot and say, yeah, that line fits the points pretty well. We're good to go. If you think it doesn't, we don't want to use it. And if the value of R is reasonably large, what is reasonable? We're not going to get too tricky on that. Um, Anything that's low, probably not good. Anything that's high, probably good. Moderate, it kind of depends. Again, not going to try to get too tricky on that. As long as you get the general concept, you should be able to successfully answer the questions thrown at you on that topic. When and how to interpret slope and y-intercept. Remember, we can always interpret the slope no matter what. Slope is as x increases by 1, y increases or decreases by whatever the slope is. Y-intercept only is interpretable when x equals 0 makes sense. The way you interpret the y-intercept is when x equals 0, this is what I expect y to be. But pause and ask yourself, does it make sense for x to be 0? If it does, carry on, and that's exactly what you want to do. But there's times when you'd say, x equals 0 doesn't make sense. Okay, right? If I'm talking about, weight of humans, right? You would say x equals 0 doesn't make sense. If you're talking about age, sure, age equals 0 makes sense, right? When you're born, your age is 0, right? So it just depends on the situation where you might say x equals 0 makes total sense. I'm going to apply that interpretation of the y-intercept and say, yeah, when x equals 0, I expect y to be this. But there's times when you say x equals 0 doesn't make sense, and I would say it's not appropriate to interpret the y-intercept. Difference between y hat, and y bar. Remember that y is the actual value. Y bar is the mean of the values. Y hat is the predicted value. And our regression equation always, 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 always needs to be written as y hat equals. Excel doesn't show you the hat when they write their equations. There are some other softwares that don't. Shame on them. Make sure you understand that when you report a regression equation, if you write y equals without the hat, you are telling me that all of the values fall on that exact line, which is almost assuredly not true, right? So we want to report our regression equations as y hat. What we're saying is I predict that y will be this falling along this line, right? When we say y equals whatever, I know this class gets really complicated. I understand that. Stop and just take a big picture view of what you're doing, right? You understand Algebra 1. That was a long time ago for some of you. I understand that, but you understand the concept of I have a line. I could draw I could draw a little axes and plot the line, right? The idea is that I say y hat equals because I'm saying there's a line and it's what I predict y to be. It's not what y actually is, because y actually are the dots on the plot, right? And so make sure you understand the dots are different than the line. The dots don't fall on the line. Maybe one or two will, sure. But the dots are what actually happened. The line is what I'm predicting as a general trend. Okay, so when we report our regression equations, we say y hat equals because we say I'm predicting this, versus saying y equals, I would say this is actually what happened, which is not true because the dots don't always fall on the line. Okay. I think the residual is the difference between the dot and the line. We build our regression equations, and what the math's doing in the background is trying to minimize those residuals. It's trying to say I want to get the line as close to those points as possible. The residual is that difference between y and y hat. It's the difference between the dot and the line. And hopefully those are relatively small. When those get really big, when the points get really far away from the line, that's when we go back to maybe I shouldn't be using the regression equation to predict, because it's not a good prediction. When those residuals are really close to the line, that's when I have a good regression equation and I can make a prediction about a future value. Okay, so that wraps us up here on this review. As always, let me know if you have questions. Best of luck studying and best of luck on the exam.